Okay, so today we're going to talk about a new section, percent composition, empirical, and molecular formulas. The things that we'll talk about in this section, what you're going to be able to learn how to do, is calculate the percent composition of a compound, calculate the empirical formula of a compound, and just distinguish or know the difference between empirical and molecular formulas. This section involves a lot of word problems, so the first thing I want to tell you is don't let the wording of these problems fool you. Like, for example, with this one, what's the percent composition of nitrogen in 1 mole of potassium nitrate? Basically, what this question is asking you, how much of the mass of potassium nitrate is just from the nitrogen? So see, like, don't let the wording of the problem fool you. Just read it, take a second, think about it, and then assess what it is that they're asking you and what you need to do. Okay, so for these problems also, one of the big things is you have to be able to write the formula correctly. So again, if you are someone that has trouble writing formulas, you might want to review the other video I put up about that, or just review some notes or homework or something. So the first thing you have to do is know the formula of potassium nitrate, which is KNO3. So this problem is asking you basically what mass of the KNO3 is just the N. So mathematically, to get the percentage of something, you have to put the part over the whole. So what this would look like mathematically is the mass of the nitrogen over the mass of the potassium nitrate. Just in general, how you find out the percentage of something, you take the part divided by the whole, and then you multiply it by 100. So in this case, the mass of the nitrogen would be the part, and then the mass of the KNO3 would be the whole, because the whole compound is KNO3, and then the part that we're concerned about is the nitrogen. Once we do our calculations and everything, and we divide the part over the whole times 100, our answer will be about 13.85%. So that's how much of the total mass of potassium nitrate comes from just the nitrogen. Okay, these are just general steps on solving percent composition problems. First thing you have to do, first thing before even the number one on here, you need to read the question. That's very important. So first thing you do after you read the question is you find the mass of the entire compound. So that means you will find the molar mass of the entire compound. Next thing you do is find the mass of just the element that you are concerned with. So for example, if we wanted to find the percent composition of, let's just say, sodium in sodium chloride, you need to find the molar mass of sodium chloride, and then you would find the molar mass of just the sodium. Next thing you do, divide the mass of the element by the mass of the compound, and then you multiply it by 100 to change it into a percentage. Okay, our first example, what is the percent composition of hydrogen in water? So we all know that water is H2O. That's a horrible H. Okay, so our molar mass of water is going to be about 18 grams. Sorry, grams per mole, rather. Okay, and then the mass of just the hydrogen. Remember, there are 2 hydrogens, so the mass of the hydrogen is going to be about 2 grams. So now we put the mass of the element, which is our hydrogen, over the mass of the total compound, which is about 18 times 100. When we do that, it comes out to about 11, if I can make the point, 11.1% of the water is hydrogen. Okay, in our next example, what is the percent composition of oxygen and carbon dioxide? Our formula for carbon dioxide is CO2. The molar mass of that is about 44 grams. It's asking us about the oxygen. Our molar mass of the oxygen, since there's two of them, is about 32 grams. So now we can do our calculation. So we put our mass of the element, which is our oxygen, over the mass of the whole compound times 100. And that comes out to about 72 point, if I can make a point, 7% of carbon dioxide is oxygen. Okay, next thing we're going to talk about is finding percent composition from experimental. So in our next example, a 0.545 gram sample of a unknown compound is analyzed. It's found that it contains this much carbon, this much hydrogen, and this much oxygen. So we need to figure out what is the percent composition of each element. Our first step is to compare the mass of each element to the total mass of the unknown. If you notice, our total mass of the unknown from the other slide is 0.545. So we're going to basically find the percentage of each element based on that. So we have our mass of the carbon over the 0.545 times 100, mass of the hydrogen over the 5.545 times 100, mass of the oxygen over the 0.545 times 100. So even though we don't know the actual chemical formula for this based on what we were given and using this method, we can still figure out the percent composition of the compound, even though, again, we don't know the actual formula. So whatever this compound is, it's 25.1% carbon, 1.5% hydrogen, and 73.4% oxygen. Now, even though in our last example we were not given the chemical formula, part of the purpose of learning about percent composition is because we can use it to figure out the chemical formula of an unknown. So like that example that I just did, if we really wanted to, we could use that information to figure out the chemical formula. So the formula that we find from an unknown or from stuff like the example I just did is called an empirical formula. And the difference between this and a regular chemical formula that you guys have normally been writing is that this one just refers to the simplest or the lowest whole number ratio of the atoms. An empirical formula is not necessarily the real formula. Like you guys have normally been writing real formulas. Now you're going to learn how to write, I guess, if you want to think about it this way, like a pseudo formula. So the empirical formula isn't necessarily the true formula of the compound. It just tells you, just in general, what is in the compound. It just gives you a general overview of what's in it and close to the real amount that's there. Like for example, the empirical formula of C6H12O6 is CH2O. Now notice that, yeah, the C6H12O6 is a lot more in detail. It gives you exactly what's in it. But this CH2O, it's just telling you in general, look, there's carbon, there's hydrogen, there's oxygen. That's just general baseline of what's in it. Same thing with this one, this diphosphorus tetraoxide. PO2 would be the empirical formula. It's still phosphorus, it's still oxygen, it's just not telling you exactly what would be in the real formula. Okay, there are some steps that we follow to figure out the empirical formula from a percent composition. First thing is that you automatically assume that you have a 100 gram sample. We use 100 because it's just easier to convert things like that and to do calculations when it's a nice round number. So for example, if something tells you that it's like 80% carbon, that 80% becomes 80 grams of carbon. Next thing you would do is convert the mass of each element to moles. If you don't remember how to do that, please review the video I posted before this one about the mole conversions, and that'll be a good refresher for you. Next step is to divide each amount of moles by the smallest number of moles that you find, and you round to the nearest whole number. You'll see what I mean in the next slide. Okay, so first example we have for empirical formulas, is a compound was analyzed and found to contain 54.1% calcium, 43.2% oxygen, 2.7% hydrogen. What's the empirical formula of this compound? Our first step in this example is to assume that we have a 100-gram sample, so all of those nice percentages we just found now become grams. So that means our 54.1% of calcium now becomes grams of calcium, grams of oxygen, and grams of hydrogen. Next step is to convert our grams to moles. Again, if you are still having trouble with that or you need a refresher on how to do that, I posted a video prior to this one about mole conversion, so take a look at it. So our mole conversions are here. Have our moles of calcium, moles of oxygen, and moles of hydrogen. Next thing we need to do is look at how many moles of each one we have. And we need to divide each amount of moles by the smallest amount we have. So if these are our amounts of moles, the smallest one in this list is 1.35. So that will be the one that we divide every other one by, because that is the smallest one in the list. So we divide all of these by 1.35. 1.35 divided by 1.35 is 1. The next one is 2, and then 2 again. Okay. Now, the numbers that we get when we divide that gives us our mole ratios for the formula, and that will also tell us what our subscripts are going to be. So the numbers that you get when you divide will be your subscripts. So if we got 1, 2, and 2, that means for every 1 calcium, there's 2 oxygens and 2 hydrogens. So our empirical formula will be calcium, and there's only 1. Remember, we don't write 1s in chemistry. There are 2 oxygens and 2 hydrogens. It's just easier to write it like this with the parentheses because it just looks a little neater and a little cleaner than writing like O2H2. This just looks better. Okay, so our next example, vitamin C contains elements carbon, hydrogen, and oxygen. It's known to contain 40.9% carbon and 4.58% hydrogen by mass. And then it's asking us what is the empirical formula. So the first thing we should do is make sure that all of our percents are changed to grams. So that means our carbon will be 40.9 grams. Our hydrogen will be 4.58 grams. And we don't know what our oxygen is. However, if we add these two together, that will give us about 45.48 grams. Remember, we assume that we have a 100-gram sample, so that means oxygen will have to be the difference between this and 100, which will make our oxygen equal 54.52 grams. That was a horrible decimal point. So that is our oxygen. Now that we have that, we can now convert all of our grams to moles. So we have our 40, this thing makes horrible decimal points, 40.9 grams. Change it to moles. 1 mole goes up here. The molar mass of carbon, which is about 12 grams, will go on the bottom. We'll set all these up first and then we'll do the actual math in a minute. Next one, we have our 4.58 grams of the hydrogen. Same setup, 1 mole on top. And the molar mass of 1 gram on the bottom. And our last one for oxygen, we have 54.52 grams of oxygen. 1 mole of oxygen on top, 16 grams of oxygen on the bottom. Now that we have these set up, we can start doing our canceling and do our math. So first one, grams and grams cancel. We're left with moles, so it's just 40.9 divided by 12, which comes out to about 3.33. And that'll be our moles of carbon. Next one, we have our grams of hydrogen will cancel. So then it's just basically 4.58 divided by 1, which is going to give us the same thing, 4.58. That's our moles of hydrogen. And then our last one, we have 5.452 grams of oxygen. Our grams of oxygen will cancel. We're left with moles. So we just divide the 54.52 divided by 16. Comes out to about 3.41 moles. So now that we have that in place, we can compare everything. Now, we have 3.33 moles, 4.58, and 3.41. The smallest one on this list is the 3.33. So that will be the one that we divide everything by. So now we're going to divide all of them by 3.33. Okay, so now that we have that, we can do our additional dividing. So now, 3.33 divided by itself is 1. Remember, we round to the nearest whole number, so 4.58 divided by 3.33, it comes out to about 1.4. If we want it to the nearest whole number, that one's also going to be 1. 3.41 divided by 3.33, it's a little more than 1. It's 1.0 something. That one will be 1 as well. Now that we've done that, remember these are going to be our subscripts for our empirical formula. So that means our ratio would be 1 carbon to 1 hydrogen to 1 oxygen. So if we know that, we can write our empirical formula as CHO. Remember, we don't write ones in chemistry, so that's why there are no subscripts for that one. So if we wanted to find out the real formula or the formulas that you guys are accustomed to writing, we have to compare the molar mass of the empirical formula to the actual molar mass of the substance. Empirical formulas are pretty helpful. However, they're just the simplest ratio of the atoms in the compound. Again, they don't tell you the actual number of atoms in the compound. They just give you a general idea of what is in it. So how we get the real formula, if the actual or the real molar mass of the compound is twice the empirical formula molar mass, then the real formula or the molecular formula is obtained by multiplying every single subscript in the empirical formula by 2. So again, if the actual molar mass is 2 times the empirical formula molar mass, so let's say the actual molar mass is 4 and the empirical molar mass is 2. That means every subscript in that empirical formula is going to get multiplied by 2. Example, the empirical formula for a substance is CH2O. Experiments show that the actual molar mass, so the real molar mass of the substance, is about 180 grams per mole. Then it's asking you what is the molecular formula or what is the real formula. The mass of the empirical formula is CH. Our first step would be to find the mass of the empirical formula. Now you were just so we have C, which is carbon, which is about 12. Hydrogen is about 1. There's 2 of them, so we multiply by 2, and then there's 1 oxygen, which is 16. Add it all together comes out to about 30. Okay, our next step is that we will compare the actual molar mass which we were given, which was 180, to the mass of the empirical formula, which is about 30. We divide those two, and it comes out to about 6. Our next step is we multiply all of the subscripts in the empirical formula by 6. So if our empirical formula was CH2O, C times 6 will be C6, H2 times 6 will be H12, and then O times the 6 will be 6. So we will go through some examples of how to do these problems in class tomorrow. So if you're not quite sure, just watch the video again. And like I said, we will do some examples together tomorrow. And of course, you guys know me, you will have lots and lots of practice with this. So thanks.